Geometry, the study of space, might seem to be the best understood of all mathematical subjects. Surely its foundations are the most secure. But when mathematicians in the 18th and 19th centuries looked hard at these foundations, they found things were not so comforting. Perhaps Euclidean geometry could be wrong. What if alternative geometries could be found? Could the nature of space itself be in doubt?
The way I have taken seems not to lead to the goal, but much rather to make the truth of geometry doubtful.
It's a strange phrase, the truth of geometry. What Gauss was interested in, when he wrote those words in 1799, was the deceptively simple question, is Euclidean geometry true? Does it correctly describe the space we live in? The answer might seem to be a simple yes. It does seem rather plausible that Euclid's geometry is true, doesn't it? But Gauss wasn't satisfied with what appears to be true.
I come more and more to the opinion that the truth of our geometry cannot be proved. Perhaps in another life we will get another insight into the nature of space which is unattainable to us now. But until then, we must not rank geometry with arithmetic, whose truth is a matter of logic, but rather with mechanics.
To understand how Gauss could doubt the truth of geometry, let's look a little more carefully at what it means to believe the Euclidean geometry is necessarily true. How could such a claim be proved? Well, there have to be some initial assumptions in order to get started. This is just what Euclid's 5 postulates are, statements we can't imagine being without. And then we'd want to reason from them to the rest of our beliefs about physical space. In that way, we would have shown that those beliefs are necessarily true, because they followed logically from our assumptions. But the difficulty that Gauss and other mathematicians recognized was not the method of reasoning, but one of these 5 postulates. No one doubted that a line could be drawn between 2 points, or that a circle could be drawn. But the 5th postulate wasn't quite so obvious.
If, in a plane, a third line crosses 2 others, and if the sum of the angles alpha and beta is less than 2 right angles, then the lines will eventually meet.
It was the necessity of having to assume this, the parallel postulate, that seems to have annoyed mathematicians down the centuries. It's not obviously true, and when one is playing for such high stakes as obtaining certain knowledge of the world, it is worrying to have to assume a not quite obvious truth. So people tried instead to prove it. That is to say, they discarded the postulate and tried to deduce it using just the remaining assumptions of Euclid. They make a sensible place from which to start. But trouble came when people tried to deduce theorems from this restricted list. The parallel postulate is really very useful, and it's hard to deduce theorems without it. People found a variety of assumptions that are equivalent to it. For instance, let's see what we can deduce about the angle sum of a triangle using the parallel postulate. If we assume the parallel postulate, then when we draw 2 parallel lines, these angles add up to 180 degrees. And so these 2 angles are equal. And likewise, for this line, these 2 angles are equal. Putting this information together, since alpha, beta, and gamma lie on a line, then alpha plus beta plus gamma is equal to 180 degrees, or 2 right angles. And conversely, by assuming that the sum of the angles is 180 degrees, we can deduce the parallel postulate. But be careful, that isn't what people were trying to do. They wanted to deduce the parallel postulate without making any other assumptions than these 4. They didn't want to make another assumption, even one as plausible as this one, about the angles in a triangle. In 1733, an Italian, Girolamo Saccheri, had pioneered the most fruitful way forward. It was his idea to consider what a geometry could be like that was different from Euclid's. He hoped to show that such a geometry could not exist. Evidently, if Euclid's is the only self-consistent geometry, it must be the true one. Saccheri in fact found that there were just two other geometries to consider. In both these geometries, Saccheri accepted the first four postulates of Euclid, but used alternatives for the fifth postulate. His first geometry was one in which there are no parallel lines, so any straight line through this point must meet this line somewhere along it. Now, if you're having difficulty imagining a geometry with no parallel lines, here's an example. On the surface of this sphere, we can imagine the straight lines as being great circles. Now let's consider a straight line parallel to this one, but through this point on the equator. The angles at these 2 points on the equator add up to 180 degrees. But as I move up the globe, the lines get closer and closer together, and eventually meet at the pole. And whatever line I draw through this point, it must eventually meet this one somewhere. So there are no parallel lines here. There's an entire geometry associated with the surface of a sphere called spherical geometry, and it was well known in the 18th century. We can even have triangles on the sphere, where each side is an arc of a great circle. But spherical geometry requires a different set of postulates from those of Euclid's geometry, so spherical geometry isn't a candidate for Saccheri's first alternative. But perhaps it's conceivable that something else could be devised. Well, it wasn't to be. Saccheri was able to show that the combination of Euclid's first four postulates and this property is untenable. It does lead to a contradiction. His second geometry was one in which there are many straight lines through P that never meet this line. To show the results of geometries like this, my straight lines will appear curved, so the pictures will look rather odd. But this second geometry proved to be much more obstinate. It simply would not go away. As the Swiss mathematician Johann Lambert wrote in 1770,
I have sought such consequences of this hypothesis to see if it did not contradict itself. From them all, I saw that this hypothesis would not destroy itself at all easily.
This is where Gauss came in. He read Lambert's book when he first went to Göttingen in 1795, and he shared with his predecessor the belief that if only this alternative hypothesis could be made to contradict itself, then at last Euclid's geometry would have been shown to be true. But as Lambert discovered, this assumption may produce strange theorems, but there does not seem to be a contradiction. For example, in this geometry, the angle sum of a triangle is always less than 180 degrees, or two right angles, and figures cannot have the same shape without also having the same size. Unexpected, but not logically impossible. Gradually, Gauss came to believe that perhaps this alternative geometry might be logically consistent. But although Gauss corresponded with those who were working on the matter, he did little to develop their ideas. To follow those who really did investigate a new geometry, we must turn to the distant corners of Europe, to Russia and to Hungary. Gauss's old student friend, Wolfgang Bolyai, had gone back to Hungary and become a professor there. His son, János, turned out to be a mathematical prodigy and learned of the problem of the truth of geometry from his father.
I entreat you to leave the science of parallels alone. I thought I would sacrifice myself for the sake of truth. I was ready to become a martyr who would remove the flaw from geometry and return it, purified, to mankind. I turned back when I saw that no man can reach the bottom of this night.
The son didn't listen, and his father tried again.
I have traveled past all reefs of this infernal Dead Sea, and have always come back with broken mast and torn sail.
Imagine his consternation when his son replied in 1823,
I have not yet made the discovery, but the path which I have followed is almost certain to lead me to the goal, provided the goal is possible. All that I can say now is that I have created a new and different world out of nothing. All that I have sent you thus far is like a house of cards compared to a tower.
In the two phrases, I have not yet made the discovery, and I have created a new world out of nothing, lies the whole story of what we can begin to call non-Euclidean geometry. For once a new geometry can be conceived, it is possible that this geometry is the true one. To determine the truth of geometry would henceforth be a task for the experimenter, and geometry would be like mechanics. But the discovery is not yet made for sure. There could still be a contradiction just around the corner. In 1831, suppressing their remaining doubts, they went ahead and published Janosch's work. It came out as an appendix to the father's book on geometry. A copy was sent to Gauss, who replied,
If I commence by saying that I am unable to praise this work, you would certainly be surprised. But I cannot say otherwise. To praise it would be to praise myself. Indeed, the whole contents of the work, the path taken by your son, the results to which he is led, coincide almost entirely with my meditations.
Understandably, Janosch never forgave Gauss for what he saw as an attempt by the most famous mathematician of the day to claim priority falsely over a completely unknown mathematician. In Russia, quite independently, a similar story was unfolding. A professor, a mathematician at the University of Kazan, Nikolai Ivanovich Lobachevsky, was also trying to prove that there was a second, logically possible geometry. In 1829, he published the first description of a non-Euclidean geometry, 2 years before János Bolyai's publication. But there was no way that János Bolyai could have known of Lobachevsky's work. So what is it that these mathematicians had achieved? Since their descriptions of non-Euclidean geometry are so similar, it's convenient to describe their work together. And because their geometry turns out to be somewhat different from that of Euclid's, we have to suspend many of our conceptions of the world and prepare to enter a new universe. Perhaps the first surprise is that Lobachevsky and János Bolyai both began by describing a three-dimensional geometry. In this three-dimensional world, they assumed that a line and a point defined a plane, and that in such a plane there are always infinitely many lines through the point that do not meet the given line. They found that on this assumption there are two really interesting lines through the point. There is one in each direction that is asymptotic to the initial line, that is, gets closer and closer to it but never meets it. These lines we call the asymptotic parallels to the initial line, so that all these lines eventually meet the baseline, and all these lines eventually diverge from it in both directions. But it's these, the asymptotic parallels, that we'll be particularly interested in. They wanted to work out the trigonometry associated with this new geometry. For example, they asked, given this distance, what is this angle, known as the angle of parallelism? And they wanted the answer as a function of the distance, a. And here's something relatively new, the use of functions to do geometry. But first, to orient ourselves, we'll turn this picture round. The initial line now becomes a perpendicular, standing on this plane, and here's an asymptotic parallel to the line. Now, in this novel geometry, they picked another point, so they got a right-angled non-Euclidean triangle with its right angle here. And through this point, they drew the asymptotic parallel to the original perpendicular. Over at this vertex, they added a tiny little hemisphere. And between these three lines, on the surface of the sphere, they drew a tiny spherical triangle. Now for the wonderful idea. Remember the spherical geometry I showed you earlier? It doesn't depend on Euclid's postulates, or indeed on any assumption we make about parallel lines. So any trigonometric formulae describing the spherical triangle are true, even in this peculiar non-Euclidean world. Now, it turns out that the shape of one of these triangles determines the shape of the other. So if we know all about the shape of the spherical triangle, it should be possible to determine the shape of the non-Euclidean triangle. So Bolyai and Lobachevsky could assume the spherical trigonometrical formulae were true, and from them deduce what formulae would describe the triangle in the non-Euclidean plane. They found they were able to deduce all they wanted about the new geometry. For example, by treating the original figure as being one of a triangle with a vertex at infinity, their formulae tell you what this angle is as a function of this distance. And that's just what was required, for that gave them the angle of parallelism. There's a wonderful extra to be got out of this. In proving their results, they made use of this bowl-shaped surface, which meets every possible asymptotic parallel to the original perpendicular at right angles. Here and here. It turns out, oddly enough, that this triangle has an angle sum of 180 degrees exactly. And indeed, any triangle we draw on this surface has an angle sum of exactly 180 degrees. So within the strange three-dimensional non-Euclidean space of Bolyai and Lobachevsky, there is also an accurate picture of two-dimensional Euclidean geometry represented on this bowl. It would seem then that Bolyai and Lobachevsky had finally resolved the problem of the status of geometry. By exhibiting what Lobachevsky called an imaginary geometry different from Euclid's, surely they had shown that Euclidean geometry was not, after all, necessarily true. But by and large, the response to Lobachevsky and Bolyai's work was poor, and in a sense, we can see why. After all, they had both proceeded from an initial assumption about parallels. Strictly speaking, their work doesn't show that that assumption is logically possible. What was required was a complete rethink, something that could embrace both the old way of doing geometry and the new ideas. The man who was to provide this was a student of Gauss, the shy but gifted Bernhard Riemann. Riemann's arguments were to revolutionize the way in which geometry was perceived. He didn't start with the belief that we all know what Euclidean geometry is, or even with the view that we know what straight lines and angles are. Riemann argued forcefully that you could do geometry on any surface, such as this pear-shaped surface. He started instead with the idea that we know how to measure length. That's something, he said, you can do in any geometry. If we have a curve on the surface, then we use the calculus to measure its length. Riemann was also able to define what a straight line is in terms of length. The straight line between 2 points is just the curve of shortest length on the surface between the points. What probably most excited Gauss, who was very impressed by Riemann's ideas, was that this new idea of what geometry is put all geometries on a par. Euclidean geometry is just now one of many geometries, the geometry of a flat surface. And what precisely is a flat surface? To see that a surface is flat, we can just step off it and look. But if we want to do geometry in Riemann's sense, we have to do it using properties that lie solely within the surface. Well, it was Gauss himself who had shown how to define what's called the curvature of a surface, in such a way that it can be determined from properties within the surface alone. When we find, as we do, that for any triangle we can draw on this surface, the angles add up to 180 degrees, that amounts to showing in Gauss's language that the surface has zero curvature. In other words, it's flat. In the same way, if we find ourselves on a surface in which the angles of every triangle add up to more than 180 degrees, then we're on a surface which has positive curvature, such as this sphere. And here's a triangle on a surface we wish to understand. It's easy enough to construct a bit of such a surface, and we say it has negative curvature because it curves towards us in one direction, but away from us in the other. But what's worrying about this surface is that when you try to extend it, it might not be able to grow beyond a certain point. That would be dreadful for any surface that was trying to be a model of even two-dimensional space, because nobody believed that space came to an end. The man who was able to overcome this dilemma was an Italian, Eugenio Beltrami. Beltrami's solution was ingenious. He observed that an atlas is as good a description of a sphere as any. if you know how the scale varies from point to point, you can work out from the atlas how far apart these points are on a sphere. So an atlas is a perfectly good description of a surface of constant positive curvature. It has some disagreeable features. For example, on this one, equal distances on the sphere appear to stretch more and more as you move outwards. Beltrami's idea was to construct an atlas for a surface of constant negative curvature. If he could construct such an atlas, then he could hope to show that there was such a surface, and that there was no problem about it stopping at a boundary. Beltrami did indeed succeed in constructing such a map, but it's the version constructed by Henri Poincaré that I'd like to show you. Like the maps in the usual atlas of a globe, distances are distorted. In this case, the whole of two-dimensional non-Euclidean space is depicted inside this disk. As I move outwards, distances appear to shrink, but that's a distortion of the map-making process. We non-Euclideans don't actually shrink, nor do we ever run up against an edge. Now, looking from above, we can see how, on this map, non-Euclidean straight lines appear as arcs of circles perpendicular to the boundary circle, or as diameters. But angles appear actual size. So you can see that in this triangle, the angle sum really is less than 180 degrees, or 2 right angles. And here, you can see that in non-Euclidean geometry, there really are 2 asymptotic parallels to this line through this point. Of course, the lines meet at the boundary, but that's a non-Euclidean analogue of the way we talk of Euclidean parallel lines meeting at infinity. So, maps like this disk indeed show that a surface of constant negative curvature exists. For the first time, mathematicians could be certain that an alternative geometry was possible. So now, not only could one doubt the truth of Euclidean geometry, one had to doubt it. But what of three-dimensional space? Could a three-dimensional non-Euclidean universe be depicted? Well, here is such a model. The whole of the non-Euclidean universe is inside this ball. Here in this slice is our two-dimensional representation with the triangle that we saw earlier in the Lobachevsky model. You can see the asymptotic parallels, which now meet the original line at the top. The asymptotic parallels appear curved because of the way the map has been made. Again, this apparent point of contact is actually infinitely far away in our non-Euclidean space, as are all the points of this enclosing sphere. And this sphere, inside the large one, is the surface which is perpendicular to all the possible asymptotic parallels to that first line. And on this surface, the angle sum of any triangle is 180 degrees. So this three-dimensional atlas confirms that a three-dimensional non-Euclidean space is possible. It now does become a matter for the experimenter to determine which geometry is the true one. Finally, going back to this model, there are 2 equivalent ways of thinking of this configuration. Either you can see it from outside as a map of the three-dimensional non-Euclidean space discovered by Bolyai and Lobachevsky, or you can see it from inside as a non-Euclidean three-dimensional space, in which we have an accurate picture of another geometry, perhaps unfamiliar to us, but logically possible, the remarkable world of two-dimensional Euclidean geometry.